diffusion coefficient, which is and I may say that this is, so I will call that tortuosity. And tortuosity in that case comes from the solution of PDEs. Many people have tried to estimate that using geometrical consideration, things like that, and so there are many definitions of tortuosity. To me, it's just the way I write that, but the key is solving the PDEs for me. First thing. So the overall macroscale flux is really something which has two effects. One is a decrease here. This is always below d beta, so tortuosity is always greater than 1. And also there is this restriction due to the fact that I'm working with a closed medium, so I have to take into account that in the system. So that's for diffusion, and for so that's classical stuff probably for most of you. And of course you have this dispersion curve, which is typical. So the Peclet number is some sort of reference velocity, reference characteristic length, and the diffusion coefficient. And if I plot the effective diffusion coefficient versus the molecular diffusion coefficient, I have this well-known curve that people have used for many cases. So in general, I have for a low Peclet number a purely diffusive behavior with a tortuosity effect below 1. Transition, which might be a problem because many, for instance, experimental devices you are here, so you have to take into account those non-linearities. And then regime, let us forget about that. But I have a dispersive regime which scales with the Peclet number to the power n, and maximum is equal to 2 in the case of a Poiseuille flow in a tube, which is called the Taylor-Harris theory. But in general, n is below 2, by the 1.8 something for arrays, structured media, and then it goes to 1 if you add more and more randomness in the system. And many people in petroleum engineering or in the hydrology sciences, they use n equal to 1, which is a correct or a crude approximation closer to 1.1 for a SAM than 1.1. That's an approximation that simplifies the life a great deal. And this is always a tensor because of this dispersion effect. And so the dispersion in the linear dispersion case, for instance, dispersion can be written under the form of something that takes into account the tortuosity effect, and then this kind of tensorial writing in which I have longitudinal dispersivity and transversal dispersivity, and if I look at that, it gives the following picture for the dispersion curves. So I have the dispersion curve for the longitudinal dispersion in the direction of the flow, and in the transversal direction I have something like that, with here almost 1 order of magnitude difference. So that's very important. Dispersion effects are very important for closed media physics because it creates some anisotropy in the system, which in many cases, especially in the codes for petroleum engineering and hydrology, are essentially taken into account under this form. So what do you think? We stopped here? So
take a break.
Yeah. Just something, I have to leave at 3 sharp.